what I would like to actually introduce in this class is a little bit of historical background and current overview of AI. So let's take a look at definition. Artificial intelligence refers to the development of computer systems that can perform tasks that would typically require human intelligence, such as visual perception, speech recognition, decision-making, and language translation. These systems use machine learning algorithms and other techniques to analyze data, learn from it, and improve their performance over time. And another question, of course, what is intelligence? Because that's quite cool to define artificial intelligence, but it's not cool to avoid talking about intelligence in general. And intelligence can be defined as the ability to acquire and apply knowledge and skills, to adapt to new situations, and to solve problems. It encompasses various mental abilities, including reasoning, problem solving, perceptions, memory, and learning. Any ideas where did I get these definitions? Yeah, exactly. It's kind of, you see the emblem here. Of course, everything was generated by ChatGPT. So you see ChatGPT right now is very popular. And again, this is an example from ChatGPT logo. Do you know these two logos on the right? So this logo is Midjourney neural network. It's basically what I use to generate this title screen. And this is another image generation neural network that you can download and run on your computer. It's called Stability Diffusion. Yeah, yes, I think Stable Diffusion, sorry. So if you can play with that, it's actually quite amazing what you can do. And you will see some examples. So next question. AI, why should I care? And this is actually a report from Goldman Sachs Global Investment Research when they assess share of industry employment by relative exposure to automation by AI. Let me explain what you're actually looking at. If you see blue, like dark blue, that means that basically this particular industry will not have a lot of automation using AI. If you see the gray one, it means that basically workers will be replaced in this industry. So in this case, for instance, for this particular thing, you will have, 25% of workers fired and replaced fully by AI. And of course, you have this middle ground, like light blue color here. And this color represents like 49% replacement or complement, as they frame it here. And that basically, let me give you an example. It's like you have your computer right now and you actually need to use your computer at work. Because without computer right now, again, come on, give it a try to find a good job. So that's the thing. So AI for this light blue will be very important, and that will be something that you need to actually do in order to be successful at job. And now, game. Where do you think we are standing? So which particular column represents science? Like natural or like life science, whatever. Which one? Like from the left, approximately. Like 10s, 11s, I don't know, 20s. Guesses? 16. So somewhere here, yeah? This one or this one? Or right, left? 16. I don't want to count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This one. Okay. Any other guesses? 8. So 8, it's this one, yeah? 1, 2, 3, 4, 5, 6, 7, 8. Okay. Good. Any other? Like short guess. Adam, what do you think? 8. Okay, so here. Okay, good. Yeah. What do you think this one actually? Well, you don't need AI at all. What industry is this one? I think reality TV will actually use a lot. You will actually see that there. Because, come on, you can generate everything there. So you don't need people anymore. Okay, let me just reveal the answer. Actually, those of you who vote for 8 were very close. So, because this is a column corresponding to healthcare practitioners and technicians. So if you're going to them biomedical engineers, you will be there. Life physics and social sciences are actually here. So again, we will have some replacement, maybe because we are talking about social science. I don't know actually where they plan to replace it, but I really recommend to read this research. I will upload it. And what architecture and engineering is basically here. So you see, we basically have no jobs without using AI. So everyone will use AI. So that's why you need to do that. And finally, my favorite one is computer and mathematics. So no replacement, but no chance to get a job without knowing AI. So that's why AI is important for you. So if you want to find and land a good job, you really need to understand what to do with that. So, and now let's talk a little bit about AI, machine learning, and deep learning. What does it mean? What's the difference between these three terms? And to be honest, I'm not a big fan of this particular differentiation, but at the same time, it's very, very common. So when we're talking about artificial intelligence, we're talking about the ability of computer to mimic human behavior. So in this case, everything that's related to the human behavior, let's say planning, let's say reasoning, logic, can be attached to AI. So it's probably the widest possible definition here. So when we talk about machine learning, it's actually a subset of artificial intelligence. And here we're already talking about learning without explicitly being programmed. So trying to understand the world in some sense. So here we have this Bayesian machine learning, we have this decision trees, we have logistic regression. So it's more or less mathematical methods. And finally, we have this another subset, deep learning. It's when a machine can extract patterns from the data. And here we have our classical convolutional neural networks, perceptrons, we have this GANs, we have a transformers, basically ChatGPT, because ChatGPT actually extracts pattern from the text corpus. We have what they're called, recurrent neural networks, sorry, and variational autoencoders. So this is more or less for you to understand the difference between AI, machine learning, and deep learning. And that's also what ChatGPT thinks. What is the difference between AI, ML, and DL? And again, artificial intelligence, machine learning, and deep learning are related terms, but they have different meanings. AI refers to development of computer systems that can perform tasks that typically require human intelligence, such as perception, reasoning, decision-making, and language translation, exactly what I meant in the previous slide. Machine learning is a subset that involves the development of algorithms and statistical models that enable computer systems to learn from and make decisions or predictions based on data without being explicitly programmed. And data learning is a subset of machine learning that uses neural networks with multiple layers to model and solve complex problems. It's particularly effective in tasks such as image and speech recognition. So yeah, now ChatGPT agrees with me, and I'm quite happy with that. Quick question. I have another thing here, AGI. Have any idea what does it mean? Nah. Any other guesses? Okay, A is definitely artificial, I is definitely intelligence. Nah, very close word, very similar word. And that's actually what you need to be afraid of, and what we need to be afraid of. What is AGI? Artificial general intelligence. It's basically the system that can learn without even seeing specific data. So it's basically what we are afraid in their movies or whatever. So Skynet is artificial general intelligence. So right now, a lot of buzz about this. If ChatGPT is artificial general intelligence, I don't think so. But again, you will hear a lot of opinions that yes, we're in danger. So it's a discussion. I will not go there. So another question, why now? Why AI is super popular right now? And I found a super cool actually plot from the company Gartner. And have you seen this curve in general without any data points there? It's so-called hype curve. Do you familiar with that? So basically what happens initially, there is so-called innovation trigger, that something is just appearing, and there is a peak on there is a hype, it's really hype, there is a peak of inflated expectations. Then at some point, actually, researchers and general public realizes that, yeah, it's not so cool. So we have these sort of disillusionments, and then we gradually actually start to apply them, maybe not as often as we saw it on the peak, but in general, we kind of see that in our everyday life. So this is called hype curve, and it exists for all technologies that you can imagine. And this is very interesting hype cycle for artificial intelligence. And here, for instance, you have this artificial general intelligence that is just at the beginning. We actually see this computer vision that is also part of AI, and of course, computer vision right now is everywhere. You have self-driving cars. Maybe they are not very good, but still, and you have a lot of applications for the computer visions. Deep learning has already passed the hype. So right now, it's more or less going towards this slope of enlightenment and plateau of productivity. But what I would like you to see here, I really recommend you to be in these particular locations. So if you want just have reliable application of your skills in machine learning, go to these intelligent applications. Basically, it's already something that you can see in commerce, in industry. So that's really, really reliable way to use your knowledge. If you want to be a little bit on hype, I would really recommend to go with a generative AI. So that's all this ChatGPT, all this Midjourney, DALL-E, and these neural networks. It's right now still growing. But if you are super interested to be at the beginning, I really can recommend to go to physics-informed AI. It's basically the models that do not blindly predict something, but they also utilize their knowledge of physics. So this is quite recent, sort of discovery, and I really highly recommend to look into that if you want to be in the front edge of AI. So, and our lab basically works more or less on deep learning. So we're a little bit here. We are trying to do, again, generative AI, and we are trying to do this physics-informed AI. We're just starting with this one. So also, again, I will recommend you to be in AI engineering. It will always quite a good way to use your knowledge. Any questions about this hype curve? Any questions why now and why you need it? Let me, in this case, ask you the following question. When do you think term AI appeared? How can you date the beginning of AI? What date or what year do you think? 1900s. It's a century. It's not a year. Guess a year. Okay, that's actually quite close. That's actually very close. Yes, very close. To be honest, if you look at the Wikipedia, the idea of AI, you can actually trace it back to the ancient Greece. But we are talking about more modern AI, and actually you are quite right. So in 1950s, we have a Turing test. Like Alan Turing proposed a test. Any idea what Turing test is? No, decoding. It's basically Enigma. It's what he's famous for, just basically decoding Nazis' Enigma machine. But again, Turing test is a little bit different already. So this was a really, really big achievement, without any doubts. But then he proposed one test that will basically explain if AI, like artificial intelligence, is good enough. Do you have any idea how to perform this test? Okay, the Turing test actually works as following. Let's say there is some barrier between me and you, and I start to talk with you, and also there is a computer there, and I start to talk with the computer, and the computer will pass the Turing test when I, as a participant, would not be able to distinguish computer from you. So I can ask whatever question I want, and I will get some replies. And then if I can say, okay, this is definitely computer, that means that it failed. But if I cannot do that, that means that Turing test is passed. So that's basically the first idea, okay, how we can compare intelligence of the humans and intelligence of the machine. So in 1955, there is basically not invention, but a suggestion to build a perceptron. You will see on the next class what does it mean. So it's basically a non-linear element of the neural network that we are using right now. And in 1956, there is a famous Dartmouth conference when all big guys meet in US and basically discuss what to do with AI, what to do with the current development of computer science. And that's exactly when actually officially the term AI started to be very popular and used in the scientific literature. So we can say that 1956, it's kind of official date of birth, year of birth for AI. So what we have then, we have 1968. We have very famous ELIZA. Do you have any idea what ELIZA is? Who is she? Okay. ELIZA is the first chatbot that basically uses artificial intelligence. This is a conversation with the bot, and ELIZA, that's basically not spoiler, it's just basically description. ELIZA is a mock Rogerian psychotherapist, and the original program was described by Joseph Weitzbaum in 1966. Oh, I think I had the date wrong. And this implementation is very modern, but basically using the same approach. And so there is a dialogue. ELIZA asking, is something troubling you? And I don't know, participant, probably women say men are all alike. Now, ELIZA, what is the connection, do you suppose? They're always bugging us about something or other. Can you think of a specific example? Well, my boyfriend made me come here. Is it important to you that your boyfriend made you come here? He says I'm depressed much of the time. I'm sorry to hear that you are depressed. It's true, I'm unhappy. Can you explain what makes you unhappy? And actually, you can see that there is, of course, it's a little bit of stupid dialogue, but you see some intelligence. And surprising thing that the inventor of ELIZA designed this bot to actually mock artificial intelligence. The purpose was to say how stupid artificial intelligence is, how stupid chatbots can be, and surprisingly, public just completely misunderstand that. So they misunderstood that. They start to say, wow, that's basically already computer is talking with me. And you imagine it's 1968. It's more than 50 years ago when computers are just magic and you have the computer talking with you. So that's actually a very, very famous example from the history of AI. And everyone is happy saying, okay, yes, we will have artificial intelligence. And that's actually the quotes from this time. With 1958, within 10 years, a digital computer will be world's chess champion. Within 10 years, a digital computer will discover and prove an important new mathematical theorem. 1965, machines will be capable, within 20 years, of doing any work a man can do. 1967, within a generation, the problem of creating artificial intelligence will substantially be solved. And in the 1970s, from 3 to 8 years, we will have a machine with the general intelligence of an average human being. I really like these predictions because they are so wrong. So we see how all this hype actually led to two very famous reports. ALPAC report, it's a report in I think this one was in US from the government because government subsidized a lot of research in AI. And Lighthill report, it's a Great Britain report. And basically, this report claimed that artificial intelligence is overhyped. It's overpromising, and we should cut the funding a lot. And that's exactly what happened. The funding was cut, and we had our first AI winter. Basically, research is slowed down. Nothing is happening until in 1918s. There is another idea how we can use this artificial intelligence and how we can actually represent this artificial intelligence in so-called expert systems. It's basically systems that can predict things. And I would say they're quite similar to our recommendation systems that we have right now in, let's say, Amazon. When you're buying something, Amazon tells you, yeah, there is another thing that you may buy. So expert systems, again, they become popular. And now, because it's about money, companies start to invest. Private entities start to invest in that because they want more money and they want to kind of to sell more stuff. Therefore, right now we have at 1980s we have a hype of expert systems. In 1985 we have first kind of modern neural network and discovery of a backpropagation algorithm. We will talk about that. But unfortunately, the bubble burst again. So unfortunately, all these expert systems are very, very unprecise, and it's really, really hard to work with them. So what we have burst of this bubble. We have so-called AI winter number 2. And during the time, still there is a research in the in this field, and we actually in 1990s we have first proper convolutional neural network, and a lot of researchers right now actually uses this neural network, at least this architecture proposed in 1990, basically 30 years ago. And yeah, and now after this AI winter is over, we start to have a massive interest in AI. Do you have any idea what happened in 1997 that actually attracted a lot of public attention to the AI and machine intelligence? Any guesses what happened in 1997? It involved a machine and a human. No, actually, autopilots were invented a little bit before that. So no, it's not autopilot, because autopilot, you can treat autopilot as something kind of just follow the rules. So you need to have some creativity from machine in order to have, okay, that's already intelligence. Any idea? Human versus machine, 1997. Come again? Actually, I think. What year? No, Star Wars is 1985. No, it's not a movie. It's a real life event. What? Exactly, 1997. It's absolutely right. It's a Deep Blue versus Kasparov, and first time in history, machine destroyed human in chess. Chess was considered to be like basically human games because so many options, so much creativity, and computer IBM Deep Blue completely, again, not completely destroyed. It was quite interesting match to observe. But yes, Deep Blue is winning, and that's after that, basically chess split into the human chess and computer chess. In 2006, the term deep learning actually appears in the University of Toronto. So they're more or less defined well by the researchers at this year. In 2011, we have again IBM. We have Watson win Jeopardy. Do you know this game? Yeah. So have you heard about this game? So it's basically, I don't know, TV show when smart people just answer the questions. And the questions are formulated in a very regular manner. So like basically what year something happened or something like that. And machine basically were able to beat the best human competitor. Again, this is a big step in AI. So in 2016, we have a quite recent, another game was completely destroyed and solved by computer, AlphaGo versus Lee Sedol. Go was considered to be impossible for computers due to amount of variations, due to amount of moves in each position. It's really insane. And classical algorithms were not able to actually go deeper than, I think, 5 or 6 steps. But with a smart AlphaGo system, I think in this case it was more or less reinforced learning, when AlphaGo played against AlphaGo and trained to be better and better, what happened, actually, AlphaGo defeated the world champion. And finally, in 2022, basically, I think 5 months ago, we have ChatGPT released, and now everyone is hyping about that right now we will be useless because ChatGPT will do everything. So that's a little bit of history. You have any questions about this, a little bit of historical background? Any ideas, comments? Okay, no. Again, it's hard to ask the questions regarding history. So why now? Again, right now we are going back to 2023, and because for now we have an enormous amount of data and we know how to work with the data. So for instance, GPT-3, it's actually previous version of the of the ChatGPT, was trained on half of terabytes of data. It's 300 billion words from the internet. and it has 175 billion parameters. And GPT-4 is actually already a new model that I think if you have a paid account in OpenAI, you can use it. Should have 1 to 10 trillion parameters. It's insane. Second of all, hardware. So we start to have a GPU, and from this particular year, it's year 2000 approximately 8, NVIDIA start to develop more and more, and not NVIDIA only, start to develop a lot of GPUs that are much faster than classical CPU computations, and there is a prediction that basically in 2025, the GPU will be 1,000 times more effective than CPU. And this is a big issue for the AI, especially considering that it's much easier to do parallelization on GPUs. So that's a big step, and that's exactly actually why first AI winter happened, because the computational power of the computers back then was not enough to really handle big problems. Now we are quite good with that. And finally, software. Actually, there is a new models and easy to use frameworks. It's like it helps a lot for just regular people to start to do AI, and you can play with the TensorFlow or PyTorch, for instance. And we will do it with the TensorFlow during this class. Okay. So do you want to have a small break, or should I continue? We can have a 5-minute break, or again, I can just go through that. It's half an hour, maybe 40 minutes more. Up to you again. Feedback, interaction. Come on. Continue. Okay, I'm fine to continue. Okay, in this case, because we're right now going to another topic that I would like to discuss during this lecture. When do I need AI? So we definitely need AI when we have a lot of data. And there are some examples, for instance, from healthcare. So especially it's become popular during the COVID time. This is example from, I think, this paper, when we see the detection of the COVID risk of the basically, what they're called, lesion, yeah, in the lungs. And why this example is very interesting, because actually this is the same patient, and the corona score, what the researchers introduced here, can be monitored through the time, and we see how this person become healthier and healthier, and eventually at the end the corona score here is 0. So basically the patient is not sick anymore. So basically by human eyes it's really hard to distinguish this particular image from this image. But by using AI, you can actually, from this CT images, you can very nicely extract the problems in the lungs associated with the COVID. And this is another example with a little bit more complex neural network architecture. And actually, I would like to go a little bit into details here, what's happening here. So there is a CT images. And then what's important is just basically to extract some important information. And we have actually no idea what information is important. That's the beauty of so-called unsupervised learning, because you don't know what to expect. And the machine itself, using encoder and decoder system, will be able to observe some interesting things, then do segmentation, again, unsupervised learning, and finally basically give some information about specific features in the city. And then what happens afterwards, you can classify that. And this is already part with the supervised learning, because you know how real things in lungs correspond to some specific sickness. So this is, again, another example from the healthcare. And healthcare is one of the most important, to be honest, fields when you can use machine learning. However, you need to be careful. Really careful when you do machine learning, because on the right you see the example from epidemiology. Sorry, and this is a paper published in Forecasting and Social Change in 2021. What do you think you can see here? What do you think this plot represents? Any guesses? Okay. Do you see this new cases? And this is the date. What? Yes, corona cases. Actually, that's actually very. This plot corresponds to a very interesting story. Researchers in Singapore decided, okay, the corona started, we will run a website basically to track number of cases. And they start to do that, and actually more and more people start to use this website. And then the researchers say, we are researchers, let's use this data to predict when pandemic will end. And that's exactly what they did. They predict that with, I think, machine learning model or something like that, that we should have no corona at the June 2020. And of course, we know that this prediction is not correct. And I really like that in this paper, the authors says that this accidental forecasting experience gave us a grounded learning about the uncertainty and difficulties of COVID-19 forecasting. It's very important when you do whatever predictions you are doing to understand that there is always uncertainty and there is always problems that may arise. And we actually, at the end of this class today, we will talk about that a little bit. When also do I need AI? One of the recent examples, I actually was not familiar with this example until very recent time, protein folding. When you have so many chances to fold the protein, and it's really, really hard to predict what happens. It's really, really hard to work with that. So DeepMind, the company in UK, very famous company, proposed so-called AlphaFold system. And actually, you see this plot is very, very telling. This paper describing AlphaFold 2 released with source code. And after that, you have absolutely enormous increase in amount of papers in literature that uses this approach, this AlphaFold. And there is actually another paper that basically discusses it, and it's called AlphaFold Mania. And when I found this paper and I downloaded, I was absolutely shocked by this number, because this is an insane number. So this paper was published in 2021, and I'm not sure how you're familiar with basically scientific literature and how basically academic writing and all these things works. But to get 6,000, almost 6,500 citations per basically less than 2 years, it's insane. So this is extremely cool example when actually AI and deep learning helped a lot, and a lot of people are using that. We can switch from the very small scale when we're talking about the protein folding to an extremely large scale. And I actually had the privilege for 7 years to work with this field, exoplanets. And do you know what exoplanets are? So it's basically planets beyond the solar system. And one of the very common way to discover them is just to basically look at the star they're orbiting around, because of course they are too small to be able that we are not able to detect them. But what we can look at the star and just constantly monitor the brightness. And when the planet actually moves in front of the star, we have some small drop in the brightness. And then if you observe that more or less regularly, you will see some period, and then you can say, okay, there is exoplanet, and actually you can estimate orbital parameters of this planet. And there is quite recent, actually not very recent, it's 2018 research, basically when they used very standard machine learning techniques in order to process these curves. Because these curves, you see, they're quite noisy, as usual in astronomy, and you need to have quite reliable method to detect these exoplanets. And actually, to be honest, I'm quite jealous, because when I used to work with that in 2010, we had no tools like that, and everything had to be done manually. So that's another example when AI can be used very efficiently. So AI is needed when we have a lot of data, but also it's needed when we have a very complex relationships between the data. And now I start to move more towards more engineering applications, and I would like to start with this computational fluid dynamics. Are you familiar with the term? So basically what's happening in computational fluid dynamics? Yeah, do you have any idea what I'm talking about? So basically you have the object, in this case it's Formula 1 car, and you simulate how air will actually move around. And Why it's important? Because like 50 years ago, when teams in a Formula One designed their cars, they actually did basically that on a racetrack. So you just tweak something and ride the car and say, okay, nah, it's not good. You just tweak it again, then drive a car again until you get more or less okay performance. Afterwards, teams started to use wind tunnels, because it's much easier to do that. You have your car, it's stationary, you put your car in the wind tunnel, just do the test and see how well performance of the car is. Unfortunately, it's very, very energy inefficient method, and also it created disbalance between the big teams and small teams. So Formula One decided, okay, we will limit amount of time teams can use, can test in the air tunnels. And actually, it was done, I think, in 1990, something around this time. So, and of course, it created a problem, because you want to use you want to make your car better and better, but now there is basically limits from the Formula One administration. So teams started to use more and more computational fluid dynamics. In this case, you don't need even to build a car. You basically create the model of the car, put it into this virtual air tunnel, basically supercomputer, and run the simulations. And smaller elements you consider there, the more precise results you will get. And the team started to fight in this area. They started to develop larger and larger and larger supercomputers. And then actually it becomes so crazy that Formula One, I think in 2018, tells everyone, stop. Now we put restrictions also on a computation in Formula One, because again, you still have these big teams like Ferrari or Mercedes, and you have something like, I don't know, Alfa Romeo, and they cannot really fight. So therefore, right now, Formula One regulates amount of computational time and amount of teraflops that you can use during the season. But still, since the limitation is only on teraflops, if you use smart algorithms that provide you with a lot of details from the small amount of data, you will be in a better position in comparison with other team that just uses like computational fluid dynamics naively without any AI. And therefore, right now, AI in computational fluid dynamics is a very popular field. And I found a very interesting paper title, Progress and Challenges in the Application of Artificial Intelligence to Computational Fluid Dynamics. And this is a very famous journal of aeronautic. I don't remember exactly what it stands for, but now I would like to play a game with you. When this paper was published? Guess a year. It's from NASA, actually. Yeah, it's from NASA, from California. So, any guesses? Don't be afraid to be wrong. 2000, good guess. What's your opinion? 95, okay. 2014? Okay. Back there? 2000? I don't know. Okay. You're so wrong. 1988. This paper is as old as I am. And this is actually completely, for me, it was super surprising to see that in 1988, they already had challenges and progress in artificial intelligence. So never underestimated the history of artificial intelligence. Right now, we have another hype. But to be honest, in many, many fields, it was already used in 1988, 35 years ago. It's crazy. So another example from here, again, this is a very good reminder. I was really happy to see this year on the paper when I just located it. Another example, when you have a lot of data, of course, associated with the smart cities. Right now, a lot of cities get smarter and smarter. Urbanism is very important, and it's a very popular topic right now. And of course, in this case, we have enormous amount of data from the sensors, and this is just illustrations from a couple of papers. This is a smart city grid with, I don't know, a lot of communications from drones to smart grid, smart homes. And this is another example from the traffic management, when we have actually a car that need to predict the behavior, and we have this aggressive human-driven vehicle. And so again, this is very important to use artificial intelligence in this one, in this field of smart cities, because otherwise you will be absolutely overwhelmed with the amount of data that you cannot process. Now, let's move towards this real, like not real, like civil and mechanical engineering. One of the most famous field in civil engineering when you use AI is so-called structural health monitoring. So basically, you want to monitor the state of your building or the bridge all the time, but it's actually hard because what you get some information from the sensors. And how to interpret this information, how to know if this particular measure is good or bad. So therefore, AI is very, very useful in this thing because it allows you to basically get some patterns from the data. And here, I like this example. It's basically showing the concrete bridge, and there is a thermal camera looking at this bridge and try to detect hot, first of all, try to detect hot zones. And we actually see in this example, actually this is morning, this is already close to the noon, and this is already afternoon. We see, for instance, some defect here. And AI can flag that and say, okay, guys, something is wrong happening here. The temperature is not nicely homogeneous here. So therefore, we need to pay attention. And then what you also can do from that, you can actually create this like risk map. So for instance, this is also concrete slab, and green zones are safe zones, but we see some red elements basically telling us that, yeah, there is a chance that in this particular location, something may happen, crack will grow or everything will collapse. So, and here it's more or less classical pipeline, data collection, data pre-processing. We have then untrained AI algorithm that we train, and then we can evaluate our performance and say, okay, we need to monitor this bridge more closely, or we can live without this expensive monitoring system because we are confident in our bridge. So this is a very good example of the application. I think we will use one of these examples in our class in the practice session. Another example, when we have a lot of data and complex relationship, is when we design or try to understand the materials themselves. And this is a paper in Nature Communication that I had a privilege to review. And this is actually a very good paper. The researchers built this artificial two-dimensional silica glass structure when they have this different atom interacting. And what they were able to do, they were able to predict if the structure will fail under loading, or how it will fail, elastically or plastically. But most importantly, to be honest for me, and I think it's very exciting, they were able to predict the zones. You see this method that they used. The zones when you have a higher probability of failure. So the zones when the crack will grow or will initiate, and the zones where the crack will grow. And actually, they compared it with experiments and get a very, very good agreement. So that's a very nice example of using machine learning. In this particular case, it was CNN and support vector machines in microstructure characterization. And another example on the right, another Nature Communication paper from our colleagues from University of Freiburg as well. And what they did here, they try to train model to understand the different grains in the microstructure of, I think it was steel or aluminum. I, to be honest, don't remember exactly. And this was initial training, and blue and red zones are the false positives and false negatives detection. And after some training and transfer learning, we will talk about that in one of the lectures, actually the accuracy of the model become much, much better. So you see knots, for instance, what you can see, this zone has almost disappeared here as a false negative. Yeah, in general, also here you see this big blob is still here, but red, for instance, disappeared completely. So, and they used very few specimens to test, because that's quite a big problem. When we talk about the big data, we usually assume that we have access to enormous amount of data. But unfortunately, especially in mechanical engineering, in material science, you're quite often limited by the amount of samples you have. So you need to be smart how to do that, and transfer learning in particular is very, very good tool. This is another example, again, from a paper that we published on the bottom, and the similar paper published by our colleague from Zurich, when they generate materials. So right now, we do not only predict the properties, but we generate the materials. So we will talk about that also in the advanced topics in the class. So, but the idea here that you combine actually two neural networks in our example, this one G and F, and in their example, they also combine similar networks. And the idea is to create the material with the properties that you want. So it's not like you're looking at a material and, okay, this is a property that this material has. Now I'm asking you, I would like these particular properties. For instance, for the bone implant, if I have a broken bone, I would like to put something inside, but I don't want it to be the steel, because in this case, you will have an enormous mismatch between the stresses, because steel and bone have a very different Young modulus or other mechanical parameters. So what you can do with these approaches, with the generative designs, you can actually design, let's say, porous structures or two-phase structures that will have a very specific stiffness matrix, if you remember from the micromechanics. So you can really say that I would like to have a material that is very stiff in this direction, but extremely soft in these directions. And with this generative design, you can do that. And this is actually very, right now, very often used in medicine for implants, because this is very, very common topic. So AI, what is the future? And I would like here, because I have no idea what's the future of AI, I would like to cite ChatGPT. And ChatGPT says that AI is already playing an increasingly important role, and it sees a lot of future in data analysis, in modeling and simulations. That's exactly what we mentioned already in the previous slides. In optimization, it's another very famous field where we can use AI to basically optimize the systems in order to have, let's say, lower weight with the same stiffness. For design, generative design from the previous slide. Collaboration. I have no idea what ChatGPT wants to do here, but AI is also being used to facilitate collaboration between researchers and engineers around the world, allowing for more efficient sharing of knowledge and expertise. It's a little bit broad, but I think, yeah, this is a good topic. So we have a very bright future for AI. Unfortunately, I already mentioned, we already saw the two examples at least. One is the title screen of this class, and another is this prediction of the COVID. We have a lot of flaws in AI. We need to be careful with them. First of all, AI requires a lot of data. And let's play a game. What am I missing here when I say that AI requires a lot of data? What is important? Exactly. Good data, curated data. And actually, that's why ChatGPT was frozen basically in the training process from, I think, September 2021. And then all data was curated and predictions was created by the just regular human beings. So good and curated data is important because, again, do you know what it stands for? Exactly. Garbage in, garbage out, or rubbish in, rubbish out, if I think you're in UK. So it's important, super important to have a good and curated data. We have also a bias. That's a very big problem in artificial intelligence. And I have actually a recent example. I talked with one scientist, and they had a problem in medicine when they trained their neural network on the CT scans of the right leg, and then tried to use it for left one. And they had a problem because neural network kind of was absolutely shocked by seeing completely different orientation of the bones because it was trained only on the right leg and tried to be applied for the left. So that's what we call bias. And now, again, play a game. I had a query. Mad scientist performs experiment by mixing red and blue liquids. What do you think I will see on the pictures? What bias I will see? Exactly. This is the two examples. This one is a stable diffusion, things that you can run on your computer, therefore the quality of the generation is not so perfect. And this is a DALL-E, it's much more advanced neural network that OpenAI, I think, announced a year and a half ago. And actually, yeah, you see that only males can be mad scientists for some reason. And it's especially visible in stable diffusion. DALL-E actually did some steps in order, for instance, in this case, you don't have a female representations, but I generated it a couple of times and I saw that. And also you have a different skin color here. That's also important. Stable diffusion was not trained additionally. So therefore, again, bias is very important. And again, if right now we see it for the pictures, again, there is a recent medical example when you need to understand that you need to train your model on the correct data and use it for the same data types, not for the left leg when you train on the right leg. Yes. Another flaw of AI is lack of interpretability. So, for instance, on the left, this is a regular stop sign, and on this one, oh, sorry, why I'm showing here. This is left side, this is a stop sign, and this is another stop sign. Like, do you understand that this is a stop sign? Yeah, it's kind of for you as a human, it's absolutely easy. However, computer is not. So let's start with the panda. What you see? Come on, I already revealed it. What is that? What you see on the picture? What animal is it? Panda, right. What do you see here? Exactly. No, on the left it's panda, on the right it's gibbon. So unfortunately, AI doesn't agree with you. And 99.3% confidence that this is a monkey on the right. This is insane. And that's a very common problem of the neural networks. It's called adversarial, I think, attack. When you add a little bit of noise, it's very, very small noise. It's basically with a weight of 0.0. You actually, there is a small difference in the pixel color here and here, but you cannot detect that. But neural network will be completely shocked and completely wrong by using the right image, and it will say, okay, this is a gibbon. This is definitely not a panda. And the same, actually, the example is here, because the neural network treats this as a stop sign and this as a speed below 45 miles per hour. For some reason, it's decided to do that. And there is actually quite interesting example on this blindness of the neural network that actually we see in nature. When we have a bird, I don't remember what species of the bird we are talking about, and small birds, and the mama bird came to feed the bird. Small, I don't know, birds, yes, probably. They are very excited to see the mama bird. And researchers, what they did, they actually started to show the small birds different figures and different shapes. And they realized that the small birds are the excitement is the same for mama bird and just for random triangular with the two orange lines. So basically, for the vision and for the recognition of the small birds, the just random triangle with the two orange lines was absolutely the same as a mama bird. Because again, their cognitive functions or their interpretation was not yet established. So therefore, it's very similar things that happen in nature we can see in artificial networks. Here we see again the artificial based neural network completely mixing up panda and monkey. And another unpredictability, I really like this example. Have any idea? Do you have any idea who is she? Any idea? Nah, okay. So that's one of my favorite stories. Right now, we are big fans of ChatGPT. 50 years ago, people were big fans of Eliza because, oh, come on, computer is talking about that. This is a chatbot named Tai. It was actually created by Microsoft, the company that right now actually running OpenAI in some sort of. Yes, it was on Twitter in 2016, and in one day, it learned to be so bad. So I cannot show the tweets. I can show you only one tweet of this bot. We are going to build a wall and Mexico is going to pay for it. So that's a very cool example when your AI goes completely wrong. And Microsoft actually closed this bot, I think, after 3 days. And now it's basically a dead bot. And it happened just 6 years ago. So it's very, very important to be careful with what you are doing with AI, because you don't want to have the bot that will be so nasty as this particular example. And yeah, I think since we missed I think we are going close to the end of this introductory class. And yeah, I cannot leave let you go without writing our first equation. And this is our first equation. y equal to fx. And the question is to you as audience, in this equation, when we're doing machine learning, what are we looking for? Come again? Function. It's a good guess. Why? Oh, that's super smart, but not. Yeah, it would be actually quite a good guess, just out of box thinking. So we have the hypothesis that it's f. We have the hypothesis that it's y. Can we search for x? Exactly. So to be honest, in this particular equation, we can search for all components except equal sign. We can search for y. And in this case, that's what we call simulations, predictions, and classifications. So we know our data, like we know, for instance, our Formula One car model, and we would like to predict what would be the pressure gradients on different surfaces. So that's what we are saying, that simulations, it's again CNNs, like convolutional neural networks, recurrent neural networks, support vector machines, and others. We also can look for X. What task we are doing in this case? Actually, I mentioned this already in some examples. How you will call this search for X? Exactly. So optimization or generation. So we would like to try to find exact data that will match our predictions. So let's say in this case, we want to have our implant acts as a bone. We know how bone acts. So we need to find what geometry we need to apply in order to get this resulting behavior. Finally, what we can look for the function f. How you will call this problem? Modeling is more actually a y equal to, like the first example. Curve fitting. Yes, kind of. It's a valid guess. So, but my intention was to actually say that it's learning physics. So, because actually that's exactly what's happening in this physics-informed neural networks that I promoted already. What actually your model tries to understand is try to understand the physics of the process. And there are some very, very cool papers that basically show how, let's say, your model can learn Navier-Stokes equation. Maybe I'm wrong. It was not Navier-Stokes, but some of the very famous, like Poisson equation and so on. So basically, it has no idea what's happening. Just look at the data and try to understand the physics. And it's generalized so good that basically it's understand physics. And this is very, very, very cool thing. And if you have time, just look at YouTube about this physics-informed neural networks. I recently saw the video about biophysics-informed neural networks when they address also biological processes. And this is very top-notch research. And I really encourage you to at least look at that. And of course, if we put in from the easy to hard, we will start with the simulation that are relatively easy, and we go through the optimization that's harder. You remember these double architectures when we have the generation and we have the prediction. And finally, learning physics, it's really hard. There is a lot of still ongoing problems, unsolved problems, but I really hope that these physics-informed neural networks will succeed and will actually replace a lot of things that we are doing right now in a very, very straightforward and direct way. So yes, I think that's more or less the end of this introductory class. I think it's good in timing. So what I would like you to remember from this one, really give me or us, when Gerrit will be here, your feedback. So what we can improve, what we can actually change. On Thursday, we will have the practice session. We will have the setup session, basically when we will try to install everything on the computers. So bring your laptop, Windows or Linux. To be honest, we don't care. We have instructions for both of them. So I think it will be quite straightforward how to run, how to install everything using either virtual environment or Conda. Are you familiar with the virtual environment or Conda? Okay, good. That's exactly what we are going to do. We will see then, depending on how well it will go, we will adjust our schedule. So our email addresses are here. You can probably either take a photo of them, or you will actually have this presentation in Ilias. This is a QR code, I think, for Ilias. So also my website, the website of the laboratory is here. So feel free to, go and check out. And please register in Zulip with your Uni account. You also will have the link in Zulip in Ilias. You will have the link in Zulip in my website, in a group website. So if you have any problems with registering in Zulip, ask us, we will help. Zulip is very, very cool to distribute some questions and to basically have to be in touch with the students. So in comparison with emails, of course, you can always send emails, but we receive so many emails every day, so it's sometimes really, really hard. And Zulip is a specific instance on Baden-Württemberg Cloud that is only for this particular class. So that's a really nice setup. Yes, and I think on this end, I would like to end the first introductory lecture for the class of machine learning techniques in structural mechanics. And thank you for being here. And if you have any questions right now, yes. There are a couple of books recommendation in a campus system already. If you go into this HISI in one, I hate it, but yes, you will see some recommendation of the books regarding programming. I will gradually increase the number of the literature, but to be honest, I don't think the books will be especially important. What will be important that we will gradually roll out some manuscripts that we curate. Yeah, there is that's the thing. So because there is no good book that combine structural mechanics and machine learning, it doesn't exist. So what you can see if you look for structural mechanics and machine learning, something like that, you will see the compilation of the papers. And they're on quite high level. So for you, it might be a little bit too hard to understand what's going on there. So that's my role, and role of Gerrit is actually to explain what's happening, and that's exactly why we would like to have this scientific paper walkthroughs. It's very important for us. So if you are asking about the programming in Python and TensorFlow, there is a couple of examples in the campus system, so take a look. If you're asking about structural mechanics in relation to machine learning, I don't have any good book, to be honest, for that, but maybe I will be able to locate it. I tried, and no, for my knowledge, there is no. Good. Any other questions about organization of the course? If not, then we can end this session today, and I hope to see you on Thursday. I will be here with Gerrit. We will try to install all necessary packets, and we will have some already examples of the very simple models to right now to just check that everything is working correctly. And then gradually, practice after practice, we will go deeper and deeper into machine learning, but we always will try to attach it to structural engineering and civil engineering. Thank you very much.